I would like to begin the Femtet hands-on seminar now. I am Arya, your artificial voice instructor for the first half of today's seminar. Thank you for your attention. The objective of today's seminar is to learn the analysis procedures and operation methods of Femtet while actually operating it. I will provide an overview of Femtet's features in a lecture format. Let's start with the part, Introduction of Femtet's features. Let me say the aim of this program again. First, I will explain the various functions modeler, mesher, solver, and results display, following the sequence of simulation in Femtet. Next, I will introduce some useful features that are included in Femtet. Let me explain the flow of analysis in Femtet. First, we create the model shape that will be analyzed. The slide mentions defining a 3D model shape, but 2D is also available. You can use Femtet's modeler feature or create the shape using commercially available CAD software and then import it into Femtet. Once the model shape is complete, we move on to setting up the analysis conditions. This involves defining necessary parameters such as materials and boundary conditions for the analysis. Next, we perform meshing. Femtet utilizes a numerical analysis method called finite element method, FEM, where in 3D analysis, the model is divided into tetrahedral and hexahedral elements, which called mesh. After meshing is complete, calculations are automatically executed in each solver according to the defined analysis conditions. Finally, we check the analysis results. Now, I will explain the specific steps for defining the model shape, following the flow of the simulation. I will explain the process of creating a model using Femtet's modeler. The slide mentions creating primitives, which specifically involves using simple geometries like rectangular prisms and cylinders to form the general outline of the model. Next, we modify these basic shapes by cutting or filleting them to bring them closer to the desired shape for analysis. I will introduce Femtet's modifying commands later, but overall, the process is not significantly different from what you would encounter in standard CAD software. Next, I will explain how to create primitives. When you start Femtet, a ribbon menu appears at the top of the screen. You can use the menus in the primitive group of this ribbon menu to draw primitive. The specific process is as follows. For example, click on the solid command and select the type of 3D basic shape you want. A dialog window for parameter input will then appear sequentially, allowing you to enter the necessary parameters. Once all parameters have been entered, the creation of the 3D primitive will be complete. This slide lists the basic shapes that can be created in Femtet. A solid body refers to a 3D volumetric shape, and you can create 8 types of basic shapes, including rectangular prisms and cylinders. Next is the wire body, which consists of lines. You can create 12 types of basic shapes, such as straight lines and arcs. Then we have the sheet body, which is a flat body with no thickness. You can create 6 types of basic shapes, including rectangles and circles. Finally, there is the vertex body, which represents a simple point. Next, I will explain the drawing planes in Femtet. The drawing plane serves as the reference plane when creating a model. For example, 2D shapes, such as sheet bodies, are created on the drawing plane. Additionally, the extending direction of 3D shapes, such as solid bodies, is influenced by the drawing plane. For instance, in the case of a solid body like a cone, the normal direction of the drawing plane corresponds to the height direction of the cone. Specifically, when the drawing plane is the XY plane, the height direction of the cone aligns with the Z direction. Conversely, when the drawing plane is the YZ plane, the height direction of the cone aligns with the X direction. The slide illustrates this example using a cone, and it applies similarly to cylinders as well. Next, I would like to introduce the snap function, which is commonly used in modeling. In simple terms, the snap function allows you to easily capture specific coordinates of a model's features. For example, if you want to add a smaller cylinder on top of a larger one as shown in the lower left diagram, enabling the snap function for the center or centroid of the face allows you to easily select the center of the circle on top of the lower cylinder with your mouse. This means you won't need to manually enter numerical coordinates for the center of the cylinder to be added. It would make your drawing process much more efficient. This slide presents a list of the 8 snap functions included in Femtet's modeler. You can individually enable or disable each snap function based on the specific features of the coordinates you want to capture. This significantly simplifies the coordinate input for primitives and modifying commands, so please make sure to take advantage of these features. This slide shows 3 snap functions that are available only during straight-line drawing. These functions for perpendicular lines, parallel lines, and tangents make the drawing process significantly easier. Please make sure to utilize these snap functions as well. Next, I will introduce how to operate the viewpoint in Femtet. In the lower left corner of the Femtet model screen, there is a tool panel. By clicking on this tool panel, you can perform commonly used viewpoint operations such as rotating 90 degrees, moving, rotating freely, zooming in and out, and fitting the view. Please note that while Femtet 2023 had a viewpoint operation group on the Model tab of the ribbon menu, this has been consolidated into the tool panel starting with Femtet 2024. Due to time constraints, I won't be able to cover everything here, but I encourage you to check it out after the seminar. This slide summarizes the methods for viewpoint operation using keyboard and mouse operations. For rotating, zooming in and out, and moving the view, you may find that using mouse controls is more intuitive than the tool panel method introduced earlier. Feel free to try out the viewpoint operation methods that best suit your preferences. Next, I will introduce the selection process in Femtet. This operation is an area where beginners are likely to make mistakes, so we will also review it during the hands-on session later. When you need to set materials or boundary conditions, you must select specific parts of the model shape. Therefore, there are 4 selection modes available: body selection, face selection, edge selection, and vertex selection. It is necessary to switch between these select modes depending on what you want to select. You can change the select mode from either the tool panel or the drop-down menu in the ribbon menu's modification operation group. First, let me explain the difference between highlighted and selected states. The diagram on the right side of the slide shows the face has been selected. Please note how the display differs between these 2 states. When you move your mouse cursor over a face of a solid body, that face becomes highlighted in light green. The highlighted state indicates that it's a prompt for users to confirm whether they want to select that emphasized face. If you left-click while it is highlighted, that face will be selected and will turn green, while other parts remain unselected and appear white. Next, I will explain the select process. The shape near the mouse cursor is highlighted. If you want to select a face that is further back, you need to change the target to be highlighted. You can use the spacebar to switch the target to be highlighted. Pressing the spacebar will cycle through the highlighted faces from front to back. Although it's not mentioned on this slide, another method for switching highlights is through a selection list using the Tab key. When in a highlight state, pressing the Tab key will display a list of selectable options, allowing you to choose your desired face from that list. If there are many overlapping bodies and switching with the spacebar becomes difficult, please try using the Tab key for selecting from candidates. Continuing with the select process, this slide shows how to select bodies from the body tree. When you start Femtet, a body tree is displayed on the left side of the screen. The bodies created in your model are shown in a tree format, and you can select a body by clicking on the items on this tree. Next, I will introduce the area selection feature. When you drag the mouse on the model screen, a rectangle area outline with dashed lines is displayed. This function allows you to select bodies that fall within this rectangular area. There are two modes for area selection. When area selection is enabled, only those bodies that are completely contained within the area are selected. On the other hand, if area selection is not active, any body that intersects with the area, even partially, will be selected. You can choose either mode to use based on the situation. That concludes our explanation of creating model shapes using primitive geometries, viewpoint operation, highlighting, and selection. As mentioned earlier, you place basic shapes and then modify them to create the desired form in Femtet. The steps for modification involve selecting the part you want to edit using the select process introduced earlier. Then, you choose a modification command from the Model tab in the ribbon menu or from the right-click context menu. This is the basic flow of operations. For example, if you want to change the height of a cylinder, you would first select the face at its top and then execute the translation command. In the example shown on the right side of the slide, moving the top face of the cylinder in the negative z direction reduces its height. Starting from this slide, I will explain how to modify the model shape. Femtet offers a variety of modification commands for model shapes, but this slide introduces just a few. First is the Boolean function. This feature allows you to perform addition or subtraction on bodies, enabling you to combine shapes, cut them, or extract shared geometries. Next is the copy function. This allows you to create copies of a shape, and as shown in the upper right diagram, you can create copies in a matrix arrangement. Then we have the fillet function. This is a familiar feature in CAD software that making the fillet on the edges of model shapes. Finally, there is the extrude function. This enables you to extend a sheet body in the thickness direction and convert it into a solid body with a thickness. In today's seminar, we won't be able to cover all the modification commands, but I have provided a list of them. I encourage you to try out the modification commands after this seminar. This slide shows a list of modification commands categorized into Boolean operations, move, rotation, and deformation. Next, this slide presents a list of modification commands categorized into deformation, copy, conversion, and topology segmentation. For example, the last item in this list, the segment face, is necessary when you want to apply boundary conditions partially to a faces on a solid body. First, let's discuss the undo and redo functions. The undo function allows you to cancel the last modeling action, while the redo function lets you reverse that cancellation. These functions are particularly helpful when you want to revert to a previous state due to mistakes in parameter input. As shown in the lower left diagram, undo and redo operate in opposite directions. When performing undo or redo while the history tree is displayed, you can do so while having an overview of the history of body creation and modifications. The history tree keeps a record of body creation activities, allowing you to quickly undo multiple actions at once or redo all actions up to the end. This slide explains history editing. One of the features that utilizes the history tree is the history editing function. The records of body creation in the history tree not only allow you to check parameter values but also enable you to change those values later to modify or correct shapes. Using the undo function to revert back to an earlier point in history and reconstructing the model can be time-consuming. Therefore, it is more efficient to make use of this history editing feature to adjust your model as needed. Next, I will explain efficient parameter input. Femtet provides several auxiliary features for parameter input. In Femtet, if a parameter input field is left blank without any entry, the parameter input is recognized as 0. For example, if you want to set the x, y, and z components all to 0, you can simply leave the fields empty and click Next. Additionally, you can use the Tab key to navigate between input fields. This method allows for faster movement between fields compared to clicking on them with the mouse. Next, I will introduce the function for toggling the visibility of bodies. As the model structure becomes more complex and the number of bodies increases, there may be situations where you want to hide certain bodies. In such cases, please use the visibility features shown on the left side of this slide. Regarding the types of body display, you can choose between shading and wireframe modes. Both shading and wireframe displays can be set individually for each body. For example, if you only want to show the internal structure of a body, you can switch just the outer body to wireframe mode while keeping the others in shading mode. Next, I will explain the CAD data import function. If you have shape data created in CAD software, you can import that CAD data into Femtet and use it as a model shape without using Femtet's modeler feature. The formats supported by default are Parasolid format, 2D DXF format, and Gerber data. To import CAD data in other formats, you will need to implement the CAD translator option. I will briefly explain the steps for importing CAD data. To import CAD data, start by going to the File menu in the upper left corner of the Femtet screen and selecting Import CAD data. In the File selection dialog, choose the type of CAD data from the drop-down menu, select your CAD data file, and then click the Open button. Femtet supports the import of 2D DXF files as a default, but it is also possible to configure settings during the import process to create a 3D model. The slide shows a situation where, during the import of a 2D DXF file for a printed circuit board, heights and thicknesses are set for each layer. For each DXF layer, you can choose whether to load it, specify a position for creating the model, and decide whether to apply thickness. We also provide add-ins for several other CAD software packages. If you are using SolidWorks SpaceClaim, you can import data into Femtet with just one click by running the add-in. That concludes the explanation of how to define model shapes in Femtet. Next, I will explain how to set the analysis conditions and material properties. In this step, you will define the material properties of the geometries created in the previous steps, as well as specify where and how much load will be applied to those geometries. The selection of the solver and the setting of mesh conditions are done through the Analysis Condition menu. Additionally, each body will have material properties and body attributes assigned. Material properties refer to the essential information required for analysis, and these can vary depending on the solver. For example, in stress analysis, you would use Young's modulus and Poisson's ratio, while in thermal conduction analysis, you would use thermal conductivity and specific heat. Body attributes are also necessary for the analysis and are separate from material properties. These need to be set for each solver as well. For instance, in magnetic analysis, you would configure forced current. In thermal conduction analysis, you would set heat quantity. Furthermore, if using anisotropic materials, you should specify the direction of anisotropy within the body attributes. For more details, please refer to introductory courses for each solver. Next, I will explain how to set body attributes and material properties. Since body attributes and material properties are assigned to bodies, you first need to select the body. Then, right-click on it and click on Body Attributes or Material Properties from the context menu. This will open a dialog box where you can configure the body attributes and materials. Please refer to the hands-on practice session for further learning. Next, I will explain how to set boundary conditions. Boundary conditions are physical constraints applied to specific parts of a body, such as its face or edges, and are necessary when performing finite element analysis. These settings also vary depending on the analysis solver used. For example, in stress analysis, you may apply loads to the face of the body or fix them in place. In thermal conduction analysis, you may fix the temperature of a surface or set heat dissipation conditions. In fluid analysis, you may specify the flow velocity at the inlet and outlet faces of the fluid. Boundary conditions are specified on specific parts of the body. For example, as shown in the diagram, you can select a surface of the body, right-click to choose the boundary condition, and then click on Edit Data to configure the details. This will also be explained in more detail during the hands-on practice session. That concludes the explanation regarding setting material properties, body attributes, and boundary conditions in Femtet. Now let's take a look at how meshing works. Femtet uses an analysis method called the finite element method. For 3D analysis, the model must be divided into tetrahedral or hexahedral elements called meshes. Femtet's meshing is essentially automatic. However, the fineness of the mesh can be pre-specified by the user, depending on the analysis model. In general, a larger mesh size leads to shorter analysis times but results in lower accuracy, while a smaller mesh size provides better accuracy but requires longer analysis times. Additionally, as shown in the figure on the right, there is a function that allows for partial specification of mesh size. This enables achieving appropriate analysis accuracy within an acceptable timeframe by selectively refining the mesh size as needed. Femtet's meshing function includes several features designed to reduce the user's burden. First is the adaptive mesh feature. This function automatically performs mesh division and analysis repeatedly to achieve an appropriate mesh division. It is particularly useful in electromagnetic analysis. Next is the automatic Boolean feature. This function automatically removes overlapping areas between bodies. For instance, when there is a complete containment relationship, the inner body is prioritized, eliminating the need for manual Boolean removal. Finally, there is the automatic coupling feature. This function automatically aligns the mesh shapes at the contact points between bodies. With this feature, for example in stress analysis, the interface between two bodies will be automatically bonded together. In mesh division, the standard mesh size is applied. The standard mesh size is a parameter that specifies the overall mesh size for the entire model. If you check the option to automatically determine the standard mesh size will be calculated automatically. In this case, the entire model will be meshed at 1/10 of the overall dimensions shown in the lower right corner of the screen. Since this size is 1/10 of the overall dimensions, it may not be sufficient to achieve adequate accuracy in the analysis results. First, please use the standard size to confirm whether the analysis completes successfully. Once you have verified that there are no issues with condition settings, you can uncheck the automatic determination option as needed and manually reduce the standard mesh size or set partial mesh sizes to improve accuracy. This slide explains the procedure for setting partial mesh sizes. For example, as shown in the diagram, you can select a specific body and set the partial mesh size from the right-click menu. In this case, it is applied to a specific body, but partial mesh sizes can also be set for surfaces, edges, and points that make up the body shape. Note that partial mesh sizes take precedence over the standard mesh size. That concludes the explanation regarding meshing in Femtet. Next, I will introduce the functions of the solvers. Femtet has 8 solvers, and I will explain the overview of each one. First, let's introduce stress analysis. This solver includes functions for static analysis, resonance analysis, harmonic analysis, transient analysis, and buckling analysis. It can be used for various applications such as analyzing loads on structures and studying vibration phenomena. If you would like to learn more about stress analysis, please consider attending the seminar on stress and thermal analysis. Next, let's introduce thermal analysis. This solver can analyze the temperature distribution of a substrate with heat sources placed on it. In transient analysis, it is also possible to observe the temperature distribution after a specified period of time. If you would like to learn more about thermal analysis, please consider attending the seminar on stress and thermal analysis. Next, let's introduce fluid analysis. This solver can analyze the flow of fluids within channels. Additionally, by coupling it with thermal conduction analysis, it can be used for thermal fluid analysis to calculate heat dissipation while considering the effects of fluid flow. If you would like to learn more about fluid analysis, please consider attending the seminar on thermal fluid analysis. Next, let's introduce magnetic analysis. This solver can analyze the magnetic forces of magnets and the inductance of coils. In transient analysis, it is possible to analyze the fundamental characteristics of motors and perform coupled analyses with external circuits. If you would like to learn more about magnetic analysis, please consider attending the seminar on magnetic and electric field analysis. Next, let's introduce electric analysis. This solver can analyze the capacitance of dielectrics and the resistance values of conductors. In resistance analysis, it is also possible to consider the effects of plating deposition. If you would like to learn more about electric analysis, please consider attending the seminar on magnetic and electric field analysis. Next, let's introduce electromagnetic analysis. This solver can calculate the S parameters of high-frequency electrical circuits and the radiation characteristics of antennas. In transient analysis, TDR, time domain reflectometry, analysis is also possible. If you would like to learn more about electromagnetic analysis, please consider attending the seminar on electromagnetic analysis. Next, let's introduce piezoelectric analysis. This solver is designed to analyze piezoelectric phenomena. It can evaluate the electric potential generated by loads or pressure, as well as the deformation that occurs when a voltage is applied. If you would like to learn more about piezoelectric analysis, please consider attending the seminar on piezoelectric and acoustic analysis. Next, let's introduce acoustic analysis. This solver analyzes sound waves generated by driving sources, focusing on parameters such as sound pressure and velocity. It can also provide results regarding the directionality of the sound waves. If you would like to learn more about acoustic analysis, please consider attending the seminar on piezoelectric and acoustic analysis. Femtet allows for coupled analysis by combining the 8 solvers introduced so far. The left diagram illustrates an example of coupled analysis between thermal conduction and stress analysis. This enables the determination of temperature distribution and stress distribution when temperature rise occurs in a substrate due to heat sources, resulting in deformation from thermal expansion. The solvers that can be combined for coupled analysis in Femtet are shown in the right diagram. If you would like to learn more, please refer to the case studies on coupled analysis available in Femtet's help documentation. Next, let's introduce the post-process features of Femtet. There are many different ways to visualize the results, so I will provide an overview of the options available. This slide shows the stress analysis results for a container under applied pressure. The left diagram is a contour plot. It visually represents areas with equal result values, color-coded like contour lines. The red areas indicate significant displacement. To the right is a vector plot. For physical quantities that have direction, you can display vectors in terms of color, direction, and magnitude. From the orientation of the displacement vectors in the central area, it is clear that upward displacement is occurring at that point. Finally, we have a cross-section view. This allows for displaying contour plots or vector plots at specified cross-sections. In this cross-section view, you can see the contour plot of displacement at that section. Next, we have the displacement plot. In analyses such as stress analysis or piezoelectric analysis, where the shape undergoes deformation, you can visualize this deformation. You can see that the upper surface of the pressure vessel bulges outward. Following that is the maximum and minimum values section. This displays the maximum and minimum values of the results shown, allowing you to identify where these values occur within the model. Additionally, using the graphing feature, you can display the result distribution along specified edges of the model in graph form. Next, we have the streamlines display. This allows you to visualize flow lines for results that have flow characteristics, such as flow velocity or magnetic flux density. Finally, there is the directional display. This feature enables you to visualize the directionality of parameters like antenna radiation power in 3D. This concludes our overview of Femtet result display features. For more information on other functionalities, please refer to the help documentation. Finally, I will introduce 4 convenient features of Femtet: parametric analysis, batch simulation, user database functionality, and macro functionality. First, let's discuss parametric analysis. This feature allows you to assign variables to the dimensions of the model and the parameters of various conditions, automatically executing analyses by sweeping these variables over specified ranges. Parametric analysis is particularly useful in scenarios where you want to make slight adjustments to the shape and compare the results. Next, we have batch simulation. This feature allows you to register multiple projects as jobs and automatically execute analyses. It is particularly useful for running analyses in bulk overnight or during off-peak hours. Next, let's discuss the user database feature. By registering body attributes, material properties, boundary conditions, and model shapes used during analyses in a database beforehand, it becomes easier to reuse this data. The database can be created in any folder on the network, making it useful for sharing models within an organization. Next, we have the macro functionality. While programming is required, this convenient feature allows for the automation of tasks such as automatically generating complex models and extracting specific results from analysis results. Femtet supports scripting in both VBA and Python. Sample macros are available on our website for your reference. This concludes the presentation. Thank you for your attention.